Hello, my name is Willie Hendrickson, and I'm going to be talking to you today about preparation methods and examples of engineered particles. Sometimes they even work. So I'm going to move fast. I have a lot of slides today. I want to just tell you why I'm interested in particles themselves, engineered particles, is because I'm with a company called AVEKA, the AVEKA Group, and we are a company focused on particle processing, contract manufacturing, and process development. And because of that, we actually end up getting a lot of questions on how to make good engineered particles. So with that, let me get into what exactly are engineered particles. I mean, they can be something as simple as just having a size controlled, or they can be something more complex in structure, chemically or biologically activated controlled release. They're just a little bit more tougher than the normal particles that we might want to make. And the question is really, how do you even approach this? And I can tell you this slide tells it all. So long as you know the tricks, you can actually do something. So let me give you an example. I have pictures of two groups here. One of Carl Friedrich Gauss, a famous German mathematician from the 18th and 19th centuries, and a picture of my three grandchildren. And they all have this, they all know the same trick. It's a trick that Carl Friedrich Gauss came up with when he was a young student. He was actually precocious and was bothering his teacher with more and more math problems. Give me another math problem. Give me another math problem. And eventually the teacher says, well, here, why don't you add up the numbers between 1 to 100, figuring that this would keep Carl busy for a while. And he came back a minute later and said, well, the answer is 5,050. The point is both Carl Friedrich Gauss, who came up with this trick, and my grandkids, who are 11, 13, and 7, all know this trick. They can add up in their head in about the same amount of time that I just did the answer to 1 to 100 or 1 to 1,000 or any series of numbers by knowing the trick. I won't tell it to you, but it's something for you to look up. So once you know the trick, you can do some things that are pretty amazing. In particle technology, we have lots of different tricks. The picture up at the top showing the kiwi shoe polish, that's an organogel particle matrix that is formed. The two pictures of the candles burning, the one with the flame going on is producing nanoparticle carbon particles, and the one with the flame off is producing evaporated wax particles. And if you know this, you have ways of doing things that other people don't know how to do. Separating salt and pepper using electrostatics is another example. And washboarding on county roads is another example of a particle process. If you understand it, you can do things that other people can't. Well, where do you get the sources for all this knowledge? Where do you find your tricks to do this? And if you're an academic, clearly you start out with academic literature. In fact, all of us should probably start there. As you grow up and become an industrial engineer, you might be looking a lot at the patent literature. But one of the things that I found out is I still use both the first two, but general reading, YouTube, and I swear to God, How It's Made is some of the best other interesting ways of finding particle knowledge sources, because it's pretty diffuse when it's all said and done. The pictures that I have here, ranging from handling flour to make bread, to doing toners in an electrophotocopying machine, or even separating aluminum using electromagnets, are all particle processes that if you know what those tricks are, you can really do some great things. The one example that I didn't mention, the lava light, is an example of a particle process that I'm going to talk about a little bit later on in the talk. So what do you need to know? And the simple answer is you need to know just about everything if you're going to design an engineered particle and figure out how to scale it up properly. This could be something as simple as the chemical properties and the physical properties, to all the way going up to financial considerations, cost, profitabilities, and just exactly what equipment do you have available. Because if you don't know all of those things, or at least most of them, you might have some real difficulties in doing what you need to do. The other thing to think about is what I call the 4 dilemmas of the scale-up apocalypse, kind of like the 4 horsemen of the medieval apocalypse. You have the available equipment dilemma, you have the drying dilemma. Anytime you're trying to dry liquids, there's always a dilemma on how do you do this most efficiently. The mass balance dilemma and the scalability dilemma that I show some pictures of a small scale distillation system and a large scale distillation system. Boy, these things can trip you up quicker than just about anything. So really keeping these in mind as how you deal with them is absolutely important. Now, having said all of that, I gave you some ideas on how to approach this, but what are the tools that we're actually going to use? Well, in making particles, you might be looking at a number of different broad tools like granulation or drying or coating. These tools also get combined as an example, combining drying and atomization to get spray drying. I'm showing some atomization techniques, and then even seeing the other bits and pieces that are there. Knowing all of these, the more of these that you know, these are the more tools and tricks that you know, the better off you can approach this whole problem. So let's get to the examples finally. After I've chattered for quite a bit here, the examples are what we're here about today. And I'm going to give you 3 examples of cellulose fiber separation, encapsulation of omega-3 oils, monodispersed particles, and for all kinds of different reasons. And what I'm really going to focus on, the statement of the need, how we approach the problem, what went right and what went wrong. Because I can tell you, almost anytime you try to come up with a new engineered particle, you should be prepared for both the right and the wrong, because it happens again and again and again. So the first one, for preparation of cellulose fiber from corn bran, the statement of the challenge, and this was a great one. It's just scale up a proven process. And in fact, it was pretty much scaled up. All we had to do is replicate it, and it was going to just actually work without any problems at all. And the idea was to produce a high concentration of cellulose fiber that had been modified during the process to come up with high water holding properties. Now, the corn bran material that we're going to start with here, I'm showing you the composition here. And basically there's a whole bunch of things that we need to get rid of: the starch, the protein, the oils, the ash, and the water. We need to get rid of those. And so we're left down with the fiber, and then we need to separate that cellulose fiber from the hemicellulose and the lignin. And basically the pictures that I'm showing on the left side of the screen here show you the structure of a fiber, which is basically a multi-layered structure formed up of cellulose microfibrils in the TEM image that you see here. And then basically we want to separate that all apart and get that cellulose out of there and get rid of the hemicellulose and lignin. The company that we were working with had a really nice process. Basically, they took the corn bran, we slurred it in water, we enzymatically digested the starches and the fats. We used caustic to solubilize the hemicellulose and lignin. We centrifuged it, we dried it, and you can see a picture of the dried cellulose down here, and also a picture of the optical image of the fibers in solution. This was, these people had been doing this for years and years and years. They needed to have bigger volumes. We actually built a plant, and what went wrong? Just about everything. The yields were incredibly poor. The process was unbelievably inconsistent. And the water holding results, this is what we were trying to do. We're trying to modify these cellulose particles to give them high water holding capacity, were incredibly inconsistent. And the company that we were working with, it looked at us like, well, what's wrong with you? We do this all the time. Well, as it turned out, here's another one of these, perhaps one of the many dilemmas. I listed 4, but there might be another whole herd of dilemmas out there also, is that they actually really didn't know what they were doing. Their yields were incredibly poor, and their process was inconsistent. And so we were kind of left with our customers looking at us, and we're trying to figure out what's going on. And so what we did is we went back to analyze and understand just exactly what was going on. So remember, I said after we get rid of the starch and the fats and all the other things, the proteins, we're left with a fiber that consists of cellulose, hemicellulose, and lignin. Now the challenge with this is analyzing a carbohydrate structure, because they all look about the same. How do you really tell what you have when you have cellulose, hemicellulose, and lignin in there? Not easy. The analytical techniques for this are difficult. Usually it's a wet method for analyzing the thing. But we found in the literature that some people had talked about using TGA as a method of analyzing for cellulose and hemicellulose in mixtures. And lo and behold, we actually improved the process quite a bit. And if you do a very precise TGA, you can get a decomposition point for cellulose and hemicellulose that's different. You might not be able to see this, but the decomposition of cellulose is listed at 300 degrees, and the decomposition of hemicellulose is listed at about 270 degrees. And these are really tight peaks, so it's almost like taking an infrared analysis, a quantitative infrared analysis of this material. So let's just take a look at the corn bran that we started with. You can see there's a couple peaks around 270, and there's a peak around 300, 325 actually, and then there's another peak out here at 400. It turns out that this is what your corn bran looks like, and varieties of different shapes on this depending on where you get the corn bran. And after we process it, they all look like this. It turns out that it was a 70-30 mixture of hemicellulose and cellulose in the starting material, and it was a mixture of 70-30 hemicellulose and cellulose in the other material, in the product material. It turned out that our customer never was producing pure cellulose. They were always producing a hemicellulose cellulose mixture, and they didn't know it. Furthermore, the yields that were around 20%, we were actually able to get those yields up to approaching 80 and 90% because we now understood what was going on, and we were actually able to make this engineered particle by understanding what we were trying to do, as opposed to just listening to what somebody was throwing over the fence at us. It was a big heads up for us, and at the end of the day. The second example I want to show you is the preparation of microencapsulated omega-3. So here we're talking about forming a little droplet of omega-3 oil with a shell around it that's going to be a nice stable structure. There are no known methods for protecting omega-3 oils from oxidation by microencapsulation. There are people that do this, and there are millions of pounds of this stuff that are sold, but the reality is oxygen is such an incredible, has incredible diffusing power. It goes right through these shell walls that you're actually making, and you can't stabilize this stuff. But as it turns out that if we look around the world and we start looking at different things, seeds themselves actually protect omega-3 oils. So flaxseed or chia seed or poppy seeds, they all protect these oils without oxidation for years, even tens of years. You can have very good systems, very good protection. So if we look at a seed, and this is just a cross section of a corn seed, you have the endosperm, which is a lot of the starches and the proteins up here, and then you have the germ that's in the slate red. This is where the oil is, and actually the oil is located in this germ, but it's in a structure called an organelle, which I've shown at the bottom here. And an organelle is a phospholipid monolayer that's stabilized by oleosins, which are specific proteins that actually stabilize the structure. So what we decided to do is let's biomimic a seed and see if we can come up with a material that actually works well for us. So the structure that we came up with was a structure that looked like this. We had an oil core with an organelle shell, followed by some alginate, followed by some carbohydrates, followed by a fat and fiber shell on the outside. And we thought that maybe, just maybe, by mimicking what an actual seed has, we could actually get a structure that looked and acted properly. Well, what happened was the multi-layer structure that we were able to make, and this is probably one of the more complicated engineered particles that we made. We did this using atomization, spray drying methods, followed by coating processes. So fluid bed processes is basically what we were doing. We were actually to get results that were as good as the industry standard, but not better. And so, you know, the solution is this was one of these ones that we didn't have enough time. We looked at changing materials. We looked at, you know, improving on the oleosin usage to make a better organelle core on the system. And we made some progress, but we could probably get just a little bit better than the industry standard, but not as good as a seed. This is a case where, you know, sometimes these engineered particles, even when you have lots of good ideas, multi-layered structures, mimicking a seed, putting in some new materials like oleosins into the structure, you know, they're good, but, you know, it might be difficult to bring them off. And it was in this particular case. And so finally, the third structure that I'd like to look at here, or the third example that I'd like to look at, is preparation of monodispersed wax beads. And so we were going to make 4 millimeter wax beads for a bioassay end use. They needed to be sterile and they needed to have extraordinarily tight size and weight. And we are faced with here the available equipment dilemma. And let me explain this for just a second. To do this process, we're going to prill, and I'm going to show this to you in just a second. And to make big prills, which are commonly made and easy to do, relatively easy to do, require typically a tower that's somewhere in the 100 to 150 feet tall. I don't have a 150-foot tower. So our solution was, we're going to go to prilling, but we're going to do it underwater. And this is basically what we're going to do is we're going to produce a lava lamp. And we're going to use a very precise atomization method to get this tight distribution. So let me give you just a little preview on what prilling is. We typically use this for microencapsulation. And basically, if you're looking at the schematic of the piece of equipment here, we're basically taking a spray drying chamber, and instead of spraying a solution into the chamber and drying it, we're spraying a melt into it and atomizing it. So, you know, works out just fine. I mean, you can almost use the same equipment to do this. You're not using solutions but melts. You have some viscosity ranges. You've got some different atomizers that you need to have. You're having a cold temperature to freeze something as opposed to a hot temperature. You can make a lot of material in a process like this. And you can be in that range of that 4 millimeters that we want to be. Now, the challenge, once again, as I said, in order to make a 4 millimeter bead in a standard prilling tower, it's going to be big. And for this process, I don't need a big process. I don't need very many beads, and I don't have a tower. So as I said, we're going to do this underwater. So here's a schematic of what we're doing. Basically, we're making a lava lamp, a very specific lava lamp that only has half of it going on. So what we're doing is down in a hot zone of water down in the bottom, we have a nozzle here that's producing small droplets. As they go up the column, they eventually get to a cold water zone and they freeze. And instead of sinking back down like a lava lamp does, we actually take it off the top and we collect these beads. Now, this is what it looks like schematically. Let me actually show you what it looks like in reality. So here's an underwater prilling process, just the system that we set up. Let's run this slide here and see what we can see. So you can see the beads being formed down here at the bottom, the droplets being formed at the bottom. I think we'll get to a close-up here in just a second. So we've got a nozzle down here. It's producing the droplets. They're actually rising up because of the difference in densities. We go through a funnel to get into a cold water zone and they freeze. So the process is relatively simple, and in an essence, because we're doing small volumes, we could do this in a water system, and we could actually take a 100-foot tower and shrink it down to about 1.5 feet. So this was a way of really thinking outside the box. You know, just looking at your cooling parameters and what you're going to do, we were actually able to do this. And what we produced is shown here in this next slide, where you can see the picture on the left hand. These are the beads that we made, and incredibly tight distribution. We actually, in this particular case, we actually measured the size, the diameter of each bead, and we actually measured the weight of each bead. And the diameter, we could really get this down to like a 3.4 millimeter bead. I mean, it was just tight, tight, tight. But it was really interesting. We saw some fluctuations in the weight of the beads, and we couldn't quite figure this out. So we took some of the beads and we cut them in half. And you can see when we cut these beads in half, 3 of the beads, now they look just fine. But 2 of the beads, you can see small holes in the bead. And what those holes turned out to be is something that we kind of knew about, but didn't fully appreciate. That was a water inclusion. So as that fat or that polymer came out, that wax came out of the nozzle, it actually encapsulated a small amount of water and trapped it in there. So whoops. So what went wrong is the underwater prilling process produced beads of the correct size and consistency. That wasn't wrong, that was great, but it had this water inclusion, holes in there. You know, so you know, we were left with something completely unexpected. But what we found out that by doing careful vacuum drying, we could actually get the water to come out of there, and we could actually get this process to work. So even when you have a great idea, we should always be prepared for that, oh my God, what am I going to do now? Because you never know what to expect. So these are the examples that I have. This is the story that I have to tell you about how to make some beads, you know, how to think outside the box, how to kind of grapple with making complicated engineered particulates. And I'd like to say, as a summary, I'd like to say that characterization is absolutely critical for you to meet the product and customer needs. So as you saw on one of the examples where we actually developed a better method for analyzing cellulose, that was absolutely critical. I like to combine the processing methods. I mean, you should always be thinking about this. You know, if you got one method that kind of gets you there, can you bring two of them together? Particularly like the underwater lava lamp prilling option that we had. And then remember to use all the tricks that you have. I mean, the tricks are what can make or break you as a great industrial processing person for scaling up or making a fancy engineered particle, because there are the right answers out there. And then finally, be prepared to fight the four dilemmas, because they will always come around and get you. So I'd like to end my talk here. I'd like to thank you for listening to me, and I'd like to take any questions that you have for me. Thank you.